I've been seeing many AI model builders like Anthropic, Moloko, and Lightrix use Kubernetes and TPUs together for their ML infrastructure. But using Kubernetes and TPUs together, that's been a bit of a mystery to me. So I went to the source and sat down with Kavitha Gowda, the product manager for TPUs on GKE, to learn more about managing accelerators in a Kubernetes cluster. It was a great discussion, and we covered a wide range of topics from chip architectures and layouts of slices and pods to the tools to get started quickly and easily. I particularly enjoyed learning about how to think about these large-scale ML workloads together with ML infrastructure as one cohesive unit. I learned a ton from all this, and I hope you will too. So without further ado, let's get to my conversation with Kavitha. How are you doing today, Kavitha?
Hi, Yufeng. I'm doing really good. I'm super excited to talk about TPUs on GKE today. Let's go through a journey and understand why TPUs on GKE, what are the value proposition, and get you all that information that you need to make your decision and to get started on TPUs. Let's jump into it now. So as you can see, TPUs, Tensor Processing Units, are Google's custom developed ASIC circuits. What does it mean? Application-specific integrated circuit, which is designed to accelerate machine learning workloads. TPU's fourth specialty of it is actually a matrix multiplying units and has sparse cores, making them highly optimized for heavy matrix calculation found in LLMs and embedding used in recommendation models. What is MXU? I think that's what everyone keeps asking me about, right? I think everyone wants to know about it. Let's consider an image recognition model. Model will have so many filters to recognize every patterns, like the curved edges, straight lines, even some of the deep filters are like to find your eyes, etc. And each one of these are a matrix multiplication. Recognize one image. To recognize actually one image, it takes billions of MXUs. And MXU is the hardware that makes TPU so powerful. It's dedicated matrix math wizard that can perform this massive calculation in a single step, making the entire process thousands times faster and more efficient than a general purpose chip. And that is what I call it as specialized architecture for AI.
That's awesome.
TPUs, as you already know, are equipped with high bandwidth memory, which we call HBM, allowing large models and batch sizes to be processed directly on the chip, reducing data transfer bottlenecks. And TPUs are also interconnected into the parts of many chips. It can start from one and scale up all the way to hundreds and thousands of TPU using high-speed interchip interconnect and optical circuit switch networking. And this is what enables TPU to be made for AI, for all the large-scale AI training and inferencing. And we also have cost-efficient scalability. What does it mean? We do provide you different kinds of TPU obtainability and with dynamic workload scheduler, which helps you to obtain TPU in a flexible, cost-effective manner. And we do have framework versatility. TPU supports JAX, it supports TensorFlow, it supports PyTorch. It basically whatever you need to accelerate your AI workload. And then definitely the seamless ecosystem integration that we have on GKE, Vertex AI, and Cloud TPU API.
Awesome. I'm looking forward to diving into each of these points as we kind of go through this our presentation and kind of talk through all these, how the scaling works. And there's so many details around this because it really is, like you said, an ecosystem. And one of the side effects of basically, Google inventing this new technology is that there's all these new terms, right? Pods and slices and all these things that I think it's really important to make kind of clear for the audience what all these terms mean.
Definitely. I think we'll handle all of them in the next few slides. Let's go. And we just introduced Ironwood. And Ironwood, as you said, is our 7th generation TPU. And we do have Trillium that we had released last year, and then V5P, and then V4. And then there are other older generations as well. And here I just wanted to give Ironwood in our preview state. And as you can see, look at the numbers that you can see on Ironwood. Ironwood can take in a single TPU pod interconnected ICL links about 9,216 chips on them. And then you can also see how the T-flops for BF16 and T-flop for FB18 has jumped from our previous generation of TPUs. That means more power for your AI training and inferencing with increased HBM bandwidth per chip for all the data processing that's necessary or data loading that's necessary for your AI workloads. So that's our 7th generation Ironwood for you.
Yeah, and these numbers, when I first saw them, like I literally thought that it was a typo because it was such a big jump, right? It's just like you look at the previous generations and the kind of the way things were trending, and it's just like, wait, that makes no sense. It's not the jump is like too massive of a leap in terms of, you look at the peak compute, the HBM bandwidth numbers. It's just like going from, oh, we have 1,000, oh, 2,000, oh, now I have 7,000. It's like, what? Where did that come from?
Yes, definitely. It's our powerful AI chip. Let's jump as why do we need GKE for TPUs, right? GKE hides the underlying complexity of the chip architecture and relates the TPU chip power to the container-based workloads, providing best of both TPU and Kubernetes advantage. GKE exposes various different types of TPU slices, even from large-scale topologies of about 9,000 chips and consider them as a single atomic unit, ensuring optimized provisioning, scheduling for extracting maximum power of TPU, including the interconnected network performance of TPUs. And also, GKE provides the full ecosystem of products for your AI workload needs, from storage to load balancers to observability, etc. And you already know, GKE is known for its scale. Combination of TPU cost-efficient scale and GKE optimized scales comes together to support your large-scale training and inference on TPU. As you know, I think recently published that we support about 130K nodes on GKE, and that meaning your thousands and thousands of GPU chips can be used as one atomic unit for your large-scale training for all your frontier models. Let's get deep into each one of them. So in the TPU-optimized infra, what does it mean? So GKE is a platform, supports and exposes all different shapes and sizes of TPU, from the single chip to a single host to a multi-host and multi-slices. And it considers TPU slices as this one atomic unit, which is necessary for your training and inference, right? Because they're one unit. TPU can come in various different slice formations. And these slices are considered as this one atomic unit for provisioning, for understanding scale, and also for failover and resiliencies. And workloads are scheduled on these slices as this one atomic unit and managed accordingly for your scheduling to provide the cost efficiency to take the full power of TPU. That's what we call as atomic provisioning and scale. And
Amazing.
the next piece of the puzzle, we support all capacity obtainability that you have for TPU, all the way from on-demand to spot, reservation, and the cost-efficient mechanisms such as DWS Flex and Calendar and Spot. And along with that, GKE brings its own magic called Custom Compute class that helps you fall back for your workloads across this obtainability. You can have this workload running on one obtainability and you could not find enough capacity to scale. Hola, you can always go back to Spot or DWS or anything that you want. So it provides that cost efficient and also improves your obtainability with custom compute classes.
And we'll get more into those things
yes.
later on. So if folks are watching and they're not sure what some of those terms are, we'll see them in detail shortly.
Definitely. And also, we never forget storage. We provide you a full ecosystem of storage required for your AI workloads. And then a full ecosystem, including certain open source orchestrators such as Kubernetes and VLLM for AI serving models, integrated dashboards, etc., many things.
Perfect.
Let's get into understanding what does atomic provisioning mean. So here, I'm just giving you an idea of what various different kind of slice formations that TPU comes with. There's a single host TPU, there's a multi-host, there's a multi-slice. Let's dive deeper into each one of them. In a single host TPU, in GKE as a node pool, you can consider each single host as a single VM that can have somewhere from 1 chip all the way up to 8 chips, operating with 0 network latency between these chips. And this is an ideal entry point for your fine-tuning, for your interactive development, for your high-performance inference that needs just 8 chip power of a TPU. And you can, and GKE allows you to scale these TPU VMs. This is exactly like how you would, similar to the CPUs, where you have one VM, and if you need more scale for your inference workload, then it creates another VM, or depending on your horizontal pod auto-scaling, it expands into multiple VMs. Let's move on to the next scale, right? And this is the advantage of TPUs. Like, it scales, like it's built for that exponential scale, right? And here I'm showing you a multi-host TPU. In a multi-host TPU, as you can see, that there are multiple TPU VMs within the same node pool, in a single node pool. And I want to create a 16 by 16. Each VM is each VM has 4 chips. So here I have about 4 cross 4, about 16 VMs. Yeah, exactly. Yeah. It's quite a lot. So, and that's like 4 cross 4 cross 4. It's like 64 chips. I'm showing you 60. Yeah. So I'm showing you about 64 chips in here because each VM, let's say, has 4 chips, for example. And then each VM now is interconnected to all the other VMs. As we saw in single host, they were not interconnected. Now you are interconnected to get the power. This is how you scale. So now all of these are interconnected with the TPU ICI links, which provides you the high bandwidth network and then scales for your larger training workloads or larger inferencing workloads. So that's the part of, now you went from single host to multiple VMs with multi-host, and they're all connected to bring you higher power of TPUs for your workloads. That's like going from 1 to multiple. And then you can keep scaling. And this is not the only scale that you get, right? Depending on all different slices that your TPU provides, you can keep scaling. And in Ironwood that we spoke about, that you can have within the single node pool, you can have about 9,216 chips, right? And then all interconnected with within each other and providing
so that's
this
like this view,
system.
But like much bigger. But it's still connected in a similar fashion, just much larger.
Interconnected. And then next comes is your multi-slice TPU. So you have multi-host TPUs are within one node pool of GKE. Multi-slice is connecting multiple node pools within GKE, and that connects to the TPU slicing system. And in this case, I have one slice in node pool 1, another slice in node pool 2. And then I want a workload that needs high power of both the slices, let's say. In that case, I just say I want multi-slice TPU. And then here what we do is the node pool 1 and node pool 2, they are connected over the data center network. Each TPUs within the node pools are connected with the high bandwidth ICI link connection of TPUs. And then between these node pools, you go over the data center network. And this way you can keep attaching and going, create 50K chips, 50K chips, multi-slice TPUs on GKE, or 100K chips, whatever that you want for your massive AI training and inferencing. So that's the multi-slice TPU, basically.
Amazing. So, and I think the big thing here, right, is just that distinction between which parts of this multi-slice network, like you described, is connected over that data center network versus what's connected within each node pool. And as folks
Yes.
are designing and thinking about kind of how their workload is kind of shaped and how they're designing their code to scale across this, these large, massive
Yes.
compute infrastructures, right? Like where there is high speed and where there's slower speed, like they have to think about that in terms of where they're placing their workloads so that it can match the infrastructure. We're really seeing this combination of having to have knowledge of the software as well as the hardware in order to kind of be able to take full advantage of these systems.
Definitely. And also by leveraging GK's job set and multi-slice networking, you gain an atomic failover model where you have one slice 50K chips. Even if one VM fails for your training job, the entire thing goes down, right? Because it needs all of these chips to be up and running. There's all of these
Yeah.
VMs to be up and running. So TK considers them with job set and its technologies as this one atomic unit and tries to auto repair these TPU slices as this one atomic unit, and then helps you resume your training if one infrastructure fails, repairs, and then restarts your job so that it can restart automatically. That way you can obtain the maximum training time on these GPU chips, the expensive
Yeah.
chips that you bought. We can maximize your utilization of these chips. And that's what we call this as goodput. And we say that we aim to provide higher goodput with GKE with TPUs. And we have so many technologies to help you do with that.
That's very cool. Yeah. Not just throughput, good put.
Yes, goodput. Yes. Awesome. And then this is just a very quick understanding of all the support of all the TPU obtainabilities that we have. You already
Uh-huh.
know the cuts are nothing but reservations, which is
Okay.
your own reserved TPU capacity. And it's suitable for whatever your enterprise needs, from extreme large scale to your online inferencing to your small batch, whatever you like to, because this is your reserved TPU capacity. But then we have
Okay. What
introduced,
does CODES stands for? Do you know offhand by
I
any
think
chance?
it's a committed. I
Oh,
think
okay. It's
it's
community use discounts. Yeah. Yeah.
yes, committed use discounts, exactly.
Awesome.
And next comes is the new kind of obtainability that we released this in 2025 is the dynamic workload scheduler. And it comes with two
Oh, cool.
flavors. One is called Flex Start mode. The other one is calendar mode. The Flex Start is basically a time flexible experiments for fine tuning, batch inference, for training if you want to. You get uninterrupted VMs up to 7 days. And then
Up to
this is for,
7 days. Okay.
yes, yes. And then this
Okay.
is a pay as you go model. So
Mm-hmm.
whenever you're using, you get billed, otherwise, you do not get billed. And GKE supports this dynamic workload scheduling by auto scaling as soon as you deploy your workload in a flex model node pool. We scale only when your workloads are scheduled. Until then, your nodes are not expanded. You do not pay for your TPU chips. Only when your workload lands, workload scales, workload is running, you are billed. And as soon as your job and workload is done executing, then it scales back down and you don't have to pay anymore.
Perfect.
Yeah. And then there's another thing called calendar mode, which is basically 1 to 3 months reservation, dedicated pool, pay for your reservation during that time that you have reserved it for. This is basically for your guaranteed runtime and then optimal compact placement as well.
Cool.
And you already
Yeah.
know there's
So
on
it's
demand
like
and spot.
okay. Yeah. So I'm looking through these, right? So calendar, I'm wondering about the difference between calendar. Oh, you have a whole slide about this.
Yes. Yeah, definitely. So, for your DWS Flex is like an on-demand elasticity, right? You want your job to run, your training job or inference, you run and you scale, and then when you land your job for 7 days, you get this, you get your TPU capacity on DWS Flex, and then you pay as you go, mostly used for bursty workloads, for experimentation, for POCs, low priority job runs, etc. And then the main benefit out of this is the cost efficiency, because you're just doing pay as you go model, and it's only during your burst cases, and GKE enables you to scale or just use how much ever you want. You want to start low and then you scale and it scales back. So all the way through, you just pay for what you're running. Calendar, on the other hand, is for I want to run some training, and my training, let's say, takes fine tuning or something, runs for about 2 months or 1 month. I need it for a month or two. I would go and want to find a dedicated capacity of TPU from this date to this date. So you can go reserve your capacity, and then it's your dedicated allocation to run for that time, and that ensures you have the critical TPU resources and you're not interrupted in this reason because for maintenance or anything else. So that's the calendar reservation. And I would use DWS Flex for your burst mode. You can combine both. You can get your calendar for your dedicated, then burst into DWS capacity. Use both of them together, however you like to please, from dedicated to the burst scenarios.
Perfect. Yeah. I mean, what you were saying about kind of the calendar reservations being kind of a whole month, even with this massive infrastructure that we have, it's just like, that's just the reality, right, of some of these foundation models. They are so big and the data sets are so large. And so the importance of having reserved infrastructure like this is, like, infrastructure failure would be absolutely crippling, right? To have a training job that's running for days, weeks, and then have it fail in the middle because of infrastructure, like, not being available, that would be the worst.
Exactly. Yeah. And Canada gives you that guarantee that this capacity that you're reserving is for you for so many days that you've reserved it for. And that's just perfect when you're like, okay, I just want to do some fine tuning, some changes, some experimental runoff, some production workloads for this amount of time. And I'm done. So it's perfect.
Yeah.
And they're economically priced, and then it provides the flexibility. And that's supported on GKE completely end-to-end for TPUs.
Outstanding.
Yeah. And on top of this, to provide more economy of scale, we do support TPUs with custom compute classes. With custom compute classes, you can define prioritized hierarchy of TPU configuration. You can, in this case, I said that I need a Trillium chip and in a reservation. And if the Trillium chip is not present in the reservation when I'm trying to scale or when I'm trying to run a workload, then GKE can automatically fall back to your first fallback you've said. And that's going to be the spot here. And then if that's not available, then it goes back to the on-demand or DWS Flex, whatever that you want. And then if there's a capacity that comes back in your fallback one or in your primary, we go back to that particular capacity and try to scale up to that. Yes, primary will be your first. It's basically prioritized order of obtainability that you want to get. And this is the major advantage to jump between different obtainabilities, and either you can optimize based upon I need TPU power. Give me whichever way that's going to happen. From I have this reservation, maybe I've got this calendar, but I know something is going to burst out of here. Then I'll go to my database flex or my spot or on demand, get me anywhere, right? Or you can also optimize for cost. You'll like start with spot and then DWS flex, right? And then go back to my reservation. This may be for your low priority jobs. So you can choose whichever way you want to optimize with custom compute class, and you get this great flexibility to fall back between different kinds of obtainability.
That's super nice. I mean, I think people were like trying to basically implement this like by hand. Like they were rolling their own scripts to basically emulate this type of behavior. And so it's so super cool to see this like just introduced as a feature, because like obviously we can optimize this within GCP a lot more effectively, efficiently, and more easily, right, for the user, because now we don't need everyone to implement their own fallback system. We can just take care of, solve that problem once for everybody. I wanted to ask, how many layers of fallbacks can you have? Like we're showing 3 here, but I think you're allowed to have more probably?
You can have more for sure.
Okay,
But
cool.
I yeah, it's depends on your use cases and needs. But I think each fallback also will add some latency that you have to think about.
Sure.
So you just need to think accordingly and then place your fallbacks. And you with VLLM that we support, you can also fall back between GPUs and TPUs if you like to. I think we
Wow.
have produced some videos around this where for serving your models using VLLM model server, you can start with TPUs on reservation, and then the scale mode, you can fall back to GPUs. And then your online inferencing, real world inferencing can scale across GPUs and TPUs as well using custom compute classes.
Super cool. Yeah.
Yeah.
I think people really like that.
And with the infrastructure, as saying, we do provide these, as I was saying, the storage optimization also comes along with your TPU power for your AI workloads. And here we are showing you secondary boot disk. It's an additional persistent disk you attach to each node to preload data or container images onto the nodes, significantly improving the speed and efficiency for the pod startup. And then there's GCS Fuse, that bridge gap between object storage and traditional file system, used to load faster with caching and parallel downloads. And use GCS Fuse with CSI driver and a persistent volume claim. And with respect to parallel downloads and caching, you can gain up to 9x times faster model load time with GCS Fuse. And then definitely there's the managed Lustre. Managed Lustre is a specialized parallel file system designed to handle massive high concurrency I/O required for your data intensive training and rapid checkpointing. And then definitely our Hyperdisk ML, which is specialized engineering to eliminate the storage bottleneck with your AI lifecycle, which provides about 1.2 terabytes per second of aggregate throughput to hydrate model weights up to 12x faster than the standard persistent disk. Also, GKE also supports the other ecosystems such as Ray, KubeRay through KubeRay, and we have an add-on with the KubeRay. And as you know, Gray handles the complexity of scaling Python workload for a massive distributed systems. Data scientists work, as you know, in Python without needing to handle infrastructure, and that's the advantage of Ray. And then we bring this with KubeRay operator on GKE, and GKE handles the managed KubeRay operator, and which now supported for TPUs, and along with log and metrics. And this also supports your dynamic workload scheduler. That full ecosystem is
Perfect.
provided with other kinds of AI ML distributed workload orchestrators such as KubeRay. Awesome. And let's move on to talk more about the AI optimized scale and efficiency. And let's talk about how TPU and GKE are made for your scale, right? For large scale training and inferencing. By combining both TPU hardware with GK's orchestration, we move beyond raw performance to goodput. Goodput, the actual amount of useful training work done. GKE
Right.
handles the complexity of this atomic multi-site recovery and this automated ICI health checks, ensuring about 50K chip plus can run productive instead of stalling on individual node failures. And we do support about 130K nodes in a single notebook cluster and about 1,000 pods per second sustained scheduling throughput. That together, meaning you can scale all the way from your one chip to tens and thousands of TPU chip efficiently on GKE.
That is wild.
Yes, it is.
100,000 nodes.
Yes, it
I
is.
feel like, it's just like most people are not thinking to that level, right? But like the
Yes.
scale that some of this stuff goes to is quite intense.
Yeah. And with sustained performance and throughput, that's not easy to do. And I think that's
Definitely.
the power of GKE. And TPUs, as we saw earlier, that it can go all the way from single host, single VM to multiple VMs to it can balloon up how much ever you want. It's that exponential, there's a linear scaling that can happen on TPU. And all of that supported on GKE and managed for provisioning, for scale, and for repair as this one sustained atomic unit actually helps improve your output. That is the time, the maximizing the utilization of TPUs for your workloads. You try to run as much as possible on these chips is our aim for you at any scale.
Definitely.
Yeah, and I think we kind of bring quite a bit of ecosystem for this workload efficiencies. Job set, this is one of the thing. So GK is just not just clustered, it's like this unified AI hypercompute you can think as. Like through the energy of this GKE and job set for atomic lifecycle management, and also Q that we talk about in next few slides for a fair share resource, we provide this industrial strength foundation required to train your frontier models. JobSet provides us all or nothing orchestration. As TPU comes in slices, GKE understands the job set that it needs to schedule on all the chips to maximize utilization, and all the chips are monitored one along with your job set as this one single atomic unit, and also scaled accordingly. So that way it can support your job set on single VM all the way to multiple hosts with so many different VMs within the same node pool, and multi-slice with multiple nodes pool across. You can place your job set with across multiple node pools, which is nothing but multi-slice for your large-scale training need. So that ensuring that connectivity, atomicity, uptime running, and then maximizing the good put by reducing the recovery time between failures, and then the native support for the ML platform by providing the DNS networking, all the injection of TPU environments into your job set. All of that's been taken care of. So it's just this one orchestration for your large scale AI training or even your small scale training as well.
Amazing.
Yeah. And then comes along with Q. Now that you're now producing, you're in an organization where a lot of your ML engineers are running training workloads or job sets on this TPU, taking advantage of TPU. But you want to make sure there's a controlled way of running these jobs. You want to submit and forget.
Right.
Your ML uses, I got this, I'm done, I'm just going to submit it. Run this for me. Just submit and forget. Q takes care of these jobs, handles the rest, find the right time, right place, right resources for you to place your jobs on a GK cluster. And then you can also say different teams can have different quotas. Like one team bursting up and taking all the TPU resources and kicking off others is not a great idea. So you can also create quota management with Q, and then Q tries to make sure that the quota is met when it's trying to look for which job to place when and how. And then Q also recognizes that the TPU's uniqueness. If a customer has asked for a multi-host slice, they do want all the VMs to be running at the same time with healthy networking between them. Otherwise, you just sit and wait idly. You're like, okay, I only got 3. I asked for, let's say, 4 TPU VMs. I didn't get it. Then your jobs cannot effectively run on all of them. So it understands this gang scheduling to understand this is a single unit for your job and then place it, manage it accordingly. So that's the advantage of Q. So run your jobs with job sets, manage it across with Q with your fair share quotas and your gang scheduling that schedules effectively on TPU resources.
That's really shows kind of just how much I think, across the last few slides, we've really seen how much GKE has, whether you want to say optimized for TPUs or just
Yes.
adapted, right, to these TPU
Yes.
specific features and TPU awareness, let's call it, and not just treating it blindly as another piece of infrastructure that GKE is really pivoting to, be something that can really serve these AI workloads natively.
Exactly. And effectively. And they're optimized for the running these AI workloads. And TPU is purpose built for AI ML workloads. It comes with its own nuances. It's not like your CPUs. It's a
Right.
complete different operating model. And GKE embraces it and along brings its own advantage on top of it. GKE was known for its scale, for its optimized workload run, for efficiency, and adapts all of that into TPU nuances and boils up the TPU advantage along with the GKE advantage to get you your long-running AI workloads successful and to utilize your TPU for the maximum power. That's the goal.
Perfect. Yeah.
And comes as when you're running, so now you have your jobs. Now you got your queue to orchestrate your jobs. But then there's always an infrastructure failure. It
Yeah.
happens, and when it comes to this accelerators, they do fail because you're running many times a massive scale. And in that massive scale of 130K nodes, one node can fail or a few nodes can fail. So we do provide maximizing ML goodput with multi-tier checkpointing. So the multi-tier checkpointing eliminates the checkpointing tags. This is provided by GKE. So this it eliminates the tags of writing into the local memory first. It keeps your MXUs active and has been shown to improve your training goodput by over 6% on this massive workload run of 35K chip of TPUs. And by intelligently replicating state across adjacent nodes in the cluster, it also restores a failed job faster from the local RAM, only falling back to cloud storage as a high durability safety net when a full cluster restart is required. So this kind of capabilities helps to recover faster when something fails from your recent checkpoints, and also lets TPU, while doing checkpoint, not use maximum MXUs. It keeps MXUs running for your AI workload, and it first takes the checkpoints and moves into RAM, and then to your adjacent nodes, and then put into your cloud storage for the backup mechanism.
Very cool. Yeah. So that's the multiple tier idea of RAM,
Exactly.
local disk, cloud. Cool.
Yeah, exactly. And then comes the GKE inference gateway. So inferencing is in your real-time workload that you're running. What happens if you see on the left, that's your traditional serving model. You're using your normal load balancing. And in your normal load balancing, what happens is that, let's say you're using the VLLM, and then depending upon your input, many a times your serving takes time, right? And then so you can't really do a round robin. So as you can see in here, the first one is overloaded because it got an input that it took some time to respond to it. And then it's a round robin. If you go back with your next request, you finish the round robin, but the other ones are not so overloaded. And then the next serving comes back to the first one again. And this
Right.
increases latencies, right? Latency for your AI serving. And that is what we eliminate with the GKE inference gateway. With GKE inference gateway, we understand the VLM model serving, and we look for KV cache and the local queues of these models, and then adopt accordingly. And in this case, we saw the first one here is overloaded, right? It has a high KV cache utilization. So what happens is it understands and it goes to the VM that has lower load. And this way, we actually improve the cost of serving by 30% and reduce the latency up to 60%. This is the GKE level innovation for ensuring high quality inferencing with low latency.
Yeah, this is just another example, right, of this kind of GKE building things specifically for AI workloads. That's really clever. And in terms of like you said, different requests take different times. Somebody might be asking the model to do like some kind of deep research task that's going to take a while, and then someone else is just asking for a random fact that will be like immediate, right? Yeah.
Yes, definitely. And then there's also, and when it comes to Kubernetes, some people worry that, do I need to know Kubernetes before starting on GKE? Before running my AI info? Like, to all the great things that we have spoken about GKE until now,
Yeah.
oh my God, that looks great, but I don't know Kubernetes. I'm an ML engineer. I don't understand this. It's learning
Yeah.
this is another vector that I have to consider. But
Yeah, I
I
totally
think
feel
what
that.
I know that's quite common. So in this case, I think we have introduced different kind of experiences on GKE that can mask the complexities of Kubernetes and meet the customer wherever they are or the user wherever they are. With
Mhm.
XPK, the Accelerated Processing Kit, if you're an ML engineer, it comes with commands with pre-configured GKE cluster, pre-configured workloads. It doesn't expose you all the node pool concepts or the other YAML concepts. You just run simple commands to create your GKE cluster and just publish your workload. Just tell what model you want to run or what image you want to run, and then it'll create all of the underlying GKE necessary artifacts and deploys it for you. This is
Oh, that's
really
so
helpful for
nice.
ML engineers. Yes. Yeah, and we do see a lot of our ML engineers taking advantage of this and quickly starting up on GKE for their AI training or workloads super fast. And then obviously you have your UI. And then there's also cluster toolkit, which is more for an enterprise Terraform based blueprints for customers who are so used to Terraform. And they're like, okay, I'm just going to use Terraform blueprints to just run my AI workloads without having to know a lot about GKE clusters or GKE
Nice.
manifest artifacts. And then obviously you have GKE APIs, Terraform, G-Cloud. If you want to go to the next level to custom tune it, custom configure it, go at the scale that you want to go, etc., all of that is always there for the customer. Then the most important piece that I've kept at the last is the reliability and the resiliencies. You can see that GKE Smart Repair here features is a peace of mind for your most expensive workloads. With TPU slice from where we are talking about hundreds and thousands of chip, everything running perfectly, hours or even days of run, you do get an alert. You do have a single notebook failing in this
Yep.
giant interconnected slice, right? Then what do you
Right.
do? Right? This is basically a traditional nightmare scenario. The entire job, entire training crashes now. All your progress is lost. Your op engineers has to manually diagnose the issue, provision a replacement, restart your workloads, and then figure out what was your last checkpoint. Obviously, your workloads can have a mechanism to pull from your last checkpoint. This is a significant loss of time, money, and research momentum. And that's very expensive for an accelerator. And hence comes the GKE Smart Repair. The GKE Smart Repair gracefully shuts down the entire atomic unit, provisions a complete new healthy set of VMs to replace it, and brings the node pool back and the job set that's running, restart the job set to run on this new infra that we have created for you, and the workload resumes from its last checkpointing. And the idea is to reduce the recovery time between two interruptions. And when you reduce the time between two interruptions, you are maximizing running on the TPU. And that's the improving the throughput.
And so for something with the smart repair, do engineers need to do anything in their code to like account for this, or is GKE really doing everything out of like behind the scenes essentially?
Yeah, I think the simple scenario is GK is recognizing and understanding if your infrastructure has failed, if your TPU
Uh-huh.
infrastructure has failed, even a single node or a single VM has failed. In that case, we automatically recognize, cordon, look for a new infra that meets your workload slice need, where we can restart your VMs again, right? We can restart your workload again. There are mechanisms we also throw in between where if we get to know there's an interruption coming, then we do send a job, we do send a sick kill that we call it as sick term, which basically
Right.
tells the job if you have configured it, your pod gets some time to terminate. In that case, when you see it, you can configure time such a way that you can do checkpointing in the meantime. You can finish your checkpointing and we'll gracefully shut you down. And then when you restart, then you can start from that checkpointing so that you have less loss. It depends on kinds of signals that we get from the underlying disruption. If an immediate, we cannot do it. But let's say if it's like a maintenance disruption, definitely you can do a grace termination period and get this capability.
Great.
Yeah. And then, as you already know, GKE understands the atomic nature of TPU. And if a single node in a 3D torus mesh fails, GKE doesn't just reboot that VM, it recreates this entire multi-host slice for you to ensure that the ICI is perfectly synchronized for your training. That's basically giving you that performance that you need of the TPU, the entire TPU power. And then the job set hot swapping. The hot swapping ensures that if a TPU node becomes unhealthy, your higher priority job set is immediately rescheduled onto available spare capacity or even preempt your lower priority workloads to maintain training continuity. This eliminates that waiting period for hardware repairs, allowing to most critical AI job to reclaim healthy silicon and resume from the last checkpoint within seconds. So that's like priority-based swapping where your higher priority job set keeps running at this point.
Yeah. And the name hot swapping implies that it's like doing this kind of while it's like happening. Like this isn't like the smart repair where kind of we're dropping some stuff and then we need to find the checkpoint and all that. This is like where we're doing it live kind of thing.
Yeah, this happens when, let's say, your one of the node failed in your multi-slice, multi-host node pool, and we recognize that this can be a scenario where we don't have capacity. We don't have capacity to recreate another healthy slice for you. And in that case, it's necessary that if your job is high priority job, you want it running. This is your training job, your enterprise training job, and you have other low experimental training or other training jobs or other inference jobs that are running that are lower priority. So what this does is it cannot find capacity. It's like, okay, let me preempt this lower priority job so that I can make space for higher priority and keep running.
That's cool. Yeah.
Yeah. And we also this is also provided in terms of in queue as well that we spoke. In queue, there's also workload priority. And in the workload priority, you can say that which job set should be scheduled first. When many times the TPU or this kind of expensive, you actually want to utilize 100% of your TPU and you don't have spare capacities running around, right? It's an expensive hardware, it's hard to get by. So you're maximizing the utilization. But in this maximum utilization, you want to make sure your most important jobs gets the priority. And with queue also, you can mention the job workload priorities so that it schedules the higher priority jobs first. And if it cannot find capacity, then it kicks off the lower priority and schedules the higher priority. So all of this together provides you a greater reliability and resiliency for your peace of mind run and maximizing that goodbit for your AI workload.
Awesome.
And that's my quick summary of what are all greater things that we are bringing on GKE for TPUs and overall TPU power itself. And thank you for giving me this time, Yufeng, for showcasing this for all the cloud users.
Thank you, Kavitha. This was really insightful. I think people are going to have a lot of their questions answered here. Like people have so many questions about TPUs and GKE, and there's so many interesting features, like you said, and we'll have to dive deeper into some of these on a either on a more practical level, or we can like a lot of these individual topics. I feel like are separate videos, right? Like we can talk specifically about the scheduling system. We can talk about queue, right? Like and get into that and talk about all these, the differences of the different sizes, the slices, and the multi-host, and all these things. So there is so much to explore here, but it's also so great that GKE has these easy getting started tools for ML engineers to kind of get up and running without having to learn a whole new ecosystem of tools. Because I mean, Kubernetes is its own separate ecosystem, and I think ML engineers have spent so much time, energy, and effort to learn machine learning, right? They're not also now having to separately learn a whole new field of like DevOps and like become their own sysadmin. Like nobody wants to do two jobs, right? Their first job was hard enough. So that's super cool to see us like taking advantage of that and introducing those features like the API gateway and how GKE is aware of how TPUs work, right? And being able to schedule and hot swap and smart repair, all these things. And so like I don't like to use the word, but like this synergy, right, of GKE and TPUs to kind of really be able to work well together, and not feel like TPUs are being like, that when you're using TPUs and GKE, you don't have to like force them together. That it feels like they were made to work together.
Yes. Oh God, you put it so well. I love it. They're made to put them each other together and then run for all your needs. Yes.
Thank you so much for watching. And if you have questions for me, for Kavitha, please leave them down in the comments below. And hopefully Kavitha will have you back on. We'll make another video to talk more about this. Maybe we'll be able to answer some of folks' questions. And it'll be great. All right. So for now, we'll say goodbye. And until next time.
Please leave comments as what you like to see more and what you like to know more. And then we will try to make more videos for you so that you can get started quickly on TPUs.
We'll say bye for now.
Take care. Bye.